Books are written about sampling frequency, aliasing, and reconstruction of audio signals. I will try to illustrate them with a chirp. A chirp is a sinusoid with an increasing frequency as seen on this plot. I use a spectrogram that plots the frequency of a sound along the horizontal axis as it changes with time along the vertical axis. This is a plot of a chirp that begins at a low frequency, 100 Hz, and after 2 seconds ends with the highest frequency, 3200 Hz. This is its sound. The sampling frequency for the chirp is 8000 Hz and is enough to faithfully record the chirp over its entire frequency range. When I sample the same chirp using a sampling frequency of 4000 Hz, I get this when the audio is reconstructed. The chirp is recorded incorrectly. The recorded, then reconstructed chirp sounds correct until 2000 Hz. Then, it surprisingly decreases in frequency from 2000 Hz to 800 Hz. The reconstructed chirp frequencies above 2000 Hz are aliased, which means misidentified or given an incorrect name. Harry Nyquist was a pioneer in digitizing signals and noticed aliasing while working in Bell Labs. He wrote a paper in 1928 about the folding frequency in sampled audio. He determined that the folding frequency was half the sampling frequency. He developed the rule that for faithful recording, the sampling frequency needed to be at least twice the highest frequency in the sound. The folding frequency was later called the Nyquist frequency. Claude Shannon, also from Bell Labs, cited Nyquist's work in his paper, The Mathematical Theory of Communications, published in 1948. He proved mathematically that the sampling frequency needs to be 2 times the Nyquist frequency. And surprisingly, sampling at a higher rate does not add accuracy to the recorded signal when reconstructed back to analog. An anti-aliasing filter is put before the analog to digital converter to ensure frequencies above half the sampling frequency are blocked. Let's apply the anti-aliasing filter to the 100 Hz to 3200 Hz chirp sampled at 4000 Hz. The potentially aliased frequencies are attenuated to a degree of not hearing them, but their trace appears on the sensitive spectrogram. An anti-aliasing filter guarantees that frequencies above the Nyquist frequency are not heard, but it does not guarantee that the filtered timbre or shape of the resulting sound is desirable. Why aliasing occurs can be illustrated in the reconstruction process. A digital to analog converter, called DAC for short, converts each sample stored as a number to a voltage value. If the sampling frequency is 10,000 Hz, the DAC outputs 10,000 voltages per second. A reconstruction filter, similar to the anti-aliasing filter, inputs those voltages and outputs the desired audio signal. In this case, a 1000 Hz sinusoid was sampled at 10,000 Hz. The input sinusoid is red on the bottom graph, the samples are green, and the reconstructed analog signal is blue. If I sample a 4000 Hz sinusoid at 10,000 Hz, each cycle has 2.5 samples. But that is enough for the reconstruction filter to faithfully produce a 4000 Hz sinusoid. If I sample a 9000 Hz sinusoid at 10,000 Hz, the samples are too far apart to catch the rapid cycles. The reconstruction filter produces an A-list 1000 Hz sinusoid. A sampling frequency above 18,000 Hz would be needed to sample this signal. The range of human hearing spans 16 Hz to 20,000 Hz. To faithfully capture any sound a person with perfect hearing can hear, we need a Nyquist rate of at least 20,000 Hz, and therefore a sampling frequency of at least 40,000 Hz. Music on CDs is sampled at 44,100 Hz. Digital video production and most audio production companies sample audio at 48,000 Hz.